I wanted to say some things about Weyl groups and so on in the twisted case. So some of these things are quite elementary, and others are, I think, more or less research projects. So that seems like a good combination. There are many different possible volumes. Good. So we have this G, and so secretly that there's this B and H and this basis for each simple root space. And so this is the part which is called a pinning, and the setting that, well, this twisted case meant that there's an automorphism delta, an involutive automorphism of G, preserving the pinning. Preserving B and H, delta B is B. Delta H is H, and delta applied to the set of X alphas is the set of X alphas. So they're permuted. And anyway. So this is the same thing as an automorphism of this base root datum. Okay, and so the first, the easy thing, we have W, this Weyl group, and this has a presentation. It's generated by elements S alpha. So all right, alpha in pi. These are the simple roots. So for each simple root, there's a reflection. And this is subject to the Coxeter relations, which, all right, S alpha squared is 1, and S alpha, S beta, S alpha is equal to S beta, S alpha, S beta, where this is, well, I don't know what to say. The number of terms it is related to the bond between alpha and beta on both sides. Okay, so now in the presence of this pinning, delta gives you automatically an automorphism. In this set, it is called, S is this set of S alphas. Delta gives you an automorphism of W and S, and the twisted Kazhamustik calculations, well, I'll say that the Kazhamustik calculations are related to the Hecke algebra of W, which I talked about, well, in connection also with finite groups. So the twisted Kazhamustik calculations are related to the Hecke algebra of W upper delta. So I want to, well, this just means the fixed points of delta on W. So I want to explain why W upper delta is a Coxeter group. And well, what's its Hecke algebra? And so these are the kind of elementary things, and then things that I think need more investigation. So this is just tutorial, and then the things that I think are interesting are the relationship between W hat and representations of W over delta, and the relationship between the Hecke algebra and the Hecke algebra of W. So these are, to some extent, research problems. So that's the plan. So what's the story? So let me look at G is SL3, and delta of G is the inverse transpose of G conjugated by this element. It's alternating plus, oh, well, I can write them all out. Okay. So the Dingen diagram looks like this, and of course delta is the diagram automorphism that interchanges the two simple roots. W is excuse me, S3, which is generated by S alpha and S beta, subject to the relations S alpha squared, S beta squared is 1, and S alpha, S beta, S alpha is equal to S beta, and S alpha, and S beta. And if you look at this, if you just think about the basic facts about reduced expressions in S3, what they'll tell you is that the fixed points of delta on S3 that's exactly the elements, the identity, and S alpha, S beta, S alpha, well, which is equal to S beta, S alpha, and S beta. So if you apply delta to a reduced expression, you get another reduced expression, and in this case, you go from this reduced expression to this one, but those are equal in the Coxeter group, so that's fixed. Any smaller reduced expression goes to something that's different. So those are the only two fixed things, and and this relation tells you I don't know. Well, it's just obvious that this element has order 2. So I've presented this presents W over delta as a Coxeter group. There's a single generator. So, if we look at the general case, well, we've got this. I'm not quite sure what I should draw. There's E6, and we can. Oh, what's the Borlaki numbering of these vertices?
1, 2 up top, 3, 4, 5, 6.
Okay. So I'll just say that W over delta is generated by the following elements: S1, S6, S3, S5, S4, and S2. And these elements, well, what are the adjacency? I mean, this S1, S6, you can imagine is adjacent to S3, S5, and, well, this turns out to be a double bond to S4 and S2. And so I won't say more, but this is a Coxeter group of type F4. So that's not the general case. That's a more complicated example. And the
So what exactly are the generators of this Coxeter group?
I'm sorry?
What are the generators of this Coxeter group?
They're the ones that are written there. This is a subgroup of W, and so I can look at the group generated by these 4 elements.
So S1 and 6 is literally product of S1 and S6.
Exactly.
But in the case of SL3, it was product of 3.
Yes. So here's the story.
Because they're non-adjacent.
That's right. So the actual general case I forget what we call it. Maybe I could call it S sub delta. This is the set of orbits of 1 and delta on S. And so we write these orbits as kappa, and each kappa is either a singleton or it's two things. Those are the possibilities. And so in this case, this is an A1 subsystem. And in this case, you get either an A1 cross A1 or A2 subsystem. So in the A2 case, I had these two vertices, alpha and beta, that were interchanged by delta. So I had an A2 subsystem generated by my orbit. In this case, delta was never adjacent to, alpha was never adjacent to delta alpha, so I got A1 cross A1 subsystems. And the theorem, I don't know who this is due to. I mean, I've seen it written down in blue stick papers, but I expect it's quite old. The W upper delta, it is the Coxeter group generated by these elements T sub kappa. This is the long element of the, well, the subgroup generated by kappa. So in the A2 case, I took this length 3 reflection in S3. In the A1 cross A1 cases, I took the product of the generators, and in the A1 cases, I just took the generators.
This theorem is due to Steinberg,
Oh, thank you.
1968.
Thank you. So it's obvious that these T kappas are contained in W delta. The content of the theorem is that they satisfy the Coxeter group relations and that they generate W delta. And I mean, it's not very hard. This is not so difficult. So
What are the call them the coefficients?
So it depends. I mean, you have to look at two orbits, and so
Is it that you have to do some kind of case by case?
I think that's a good summary. There's probably a good way to write it. But if, for example,
Dan, what's the question?
what are the bond lengths in this for this Coxeter
We
group?
have an abstract.
So if you have an alpha 1 and an alpha 2, which are interchanged by delta, and a beta 1 and a beta 2, which are interchanged by delta, then what? Well, then I don't know, this kappa alpha, it has a simple bond with kappa beta. This is the diagonal subgroup in S3 cross S3. It's a boring case.
Well, so David, I think Steinberg does slightly more. So you described this as a Coxeter group. He actually describes the root system.
Okay,
And
yeah,
that answers your
yeah.
question. So it's sort of a quotient root system, and you can read it off from that.
Yeah, that's, oh,
So in particular, the bonds are the ones for the standard liquid diagrams.
Well, it's,
oh, yes, absolutely. And as Jeff indicated, this is actually a Weyl group. Sometimes the most natural way to make the root system gives a non-reduced root system. But if you have a non-reduced root system, you know, if the root lengths are 1, 2, and 4, you can just take the roots of length 2 and 4 or something, and that's a root system. Anyway.
Your construction depend on the fact that W was a one group, or would it work for
This theorem is true for a Coxeter, if you start with a Coxeter group, you get a Coxeter group. Yeah, it's using things about reduced expressions for words. That's
I think the value version of this was in physics of the 70s,
earlier than Steinberg.
early 50s.
Okay.
So they put growing up
The first name is Borel, I think. I forget. And anyway, the
first name is Jean.
okay. Okay.
So that's an example.
Yeah, that's indeed it is.
Oh, it is. Okay.
Yes.
Well, there's the F4.
Yeah, exactly. I mean, that's, yeah.
in the example you gave there, from alpha 1 value, 1 value, alpha 2, isn't the bond just simply a copy of the bond between alpha
Yes,
and
absolutely.
So it could have been a double bond.
It could have been a double bond here and here, and then you would get a double bond here. Another example, I've only talked about automorphisms of order 2 because that's what Atlas needs, but there's the marvelous triality, like this. And once exactly the same statement is true, this W of D4 upper delta is the Weyl group of type G2. You get a triple bond between this outside thing and the thing in the middle. And this is, I think, why Steinberg was interested in these questions. I think it may have been Steinberg who wanted to, I mean, he was certainly deeply involved in this. You wanted to realize an algebraic group of type G2 as this group of type D4 taking the fixed points of one of these nice automorphisms. And that's why, you know, I mean, the Weyl groups come along for the ride in this upper. So this is discussed in Springer's book about algebraic groups. He says that if you want to construct an algebraic group from a root datum, you only have to worry about the case of one root length. These cases with two root lengths all arise by folding. But if you take any diagram with two root lengths, well, like this F4, you can unfold it into E6. So this triple bond unfolds into D4. And then you can get the group construction in that way. It's a damn shame that this doesn't help you construct E8. Okay, so what did I... about representations. So, I said that, of course, this delta acts on representations of W, and I forget whether the action is always trivial. This action is, anyway, it's very often trivial. I forget the precise story. But so we can make this, maybe I'll call it delta W, this extended Weyl group. So this, you add this extra element with the relation delta squared is 1, and delta W, delta inverse is you apply the automorphism to W. And so the representations of W now are of two kinds. The first kind are fixed by delta, and these things extend in two ways to representations of this extended group. And the second case, which I think is roughly rare, you get I mean, you have some tau, which is fixed by delta, and so we tended to call these things tau plus or minus. And the rare case is these two-element orbits, tau, delta tau, and this extends to induced of tau, this induced of delta of tau. Oh, okay. And that's how you get all the representations of this. So I didn't talk about, I talked about the relation between representations of W and representations of this extended group. We're interested now in this fixed point group. So if we're given a representation of this extended group, well, let me call it, I don't know, E and E. I can write it as E plus direct sum E minus, where these are the eigenspaces of delta. And what's clearly true is that this centralizer of delta, sorry about this is the fixed points of delta, this acts on E plus and E minus. And so you can get a virtual representation of W upper delta, which is E plus minus E minus. Oh, that notation is really terrible because of this. Arg. It's the end of the conference. I'm not going to fix it. What you get is 0 if E is induced. That's kind of obvious. If not, this depends up to sign on this chosen extension. So I said when you could extend a representation tau to this extended group in two different ways, the two deltas involved, each is the negative of the other. So these two spaces just get interchanged And so the representation of W upper delta we're talking about is either a representation or it's negative. So let me look at this example, A2. So we have S3, and this is delta, and all three representations are fixed. And I'll just say, in this case, E plus minus E minus is plus or minus the trivial of W upper delta. Oh, sorry, S3. In this case, this E plus minus E minus is plus or minus the sign representation of W upper delta. And in this case, E plus minus E minus is 0. Even though it's not an induced, it's not an induced representation. I'm not sure. Anyway, that's the story. And what you see is that these guys are plus or minus irreducibles. So I'll just do S4.
Sorry, Dave, I'm a little confused. This third case, that's two representations of W over delta?
No, see, this is my bad notation. I'm taking a single representation. This is two representations of shoot. Now what I've said is just wrong. This is incorrect. This is incorrect.